Another thing which I have forgot to mention, that is you must check this AS minimum as well, along with all the AS required. That is for beam, that is 3 root FC prime BWD divided by Fy, and which should be obviously greater than or equals to 200 BWD divided by Fy. And keep remembering one thing, that in this case which BW you will be using. So if it is rectangular beam, obviously you will be using the web, and even for the T-beam as well, you will be using the width of the web for any T-beam. Say for example, if it is the T-beam, even then you will be using this BW instead of using this BF, although in all other calculations we will be using the compressive area BF while calculating in T-beam, or flange width, or for L-beam as well. But whenever you will be calculating AS minimum, keep remembering that you must use this web width as BW in all cases. So that is what you will have to do, and you will have to check that whether this AS minimum governs in any case or not. So if you see that in any case this AS minimum is governing, then that will be replacing that AS required in that case. And in after all the AS required has been obtained, then you will see whether AS minimum is governing or not. If it is governing, then you will have to provide accordingly, otherwise you will be going for the AS required, and maximum is required for negative. You will be using it for all the beams. So I will be giving you this suggestion, that if you have got a building plan like this, for example, listen carefully. So if you have got a building plan like this, so how many 2D frame you will be obtaining? This is a building plan. In that case, obviously you will be obtaining 1, 2, 3, 4, 5, 6, 7, 8. So 8 frames will be there. So if your building plan is like that, so in that case, for each frame you will be getting, say, this kind of frame you will be obtaining based on the story number you have. So for each frame, these will be your beams. So what you will have to do, that you will have to keep remembering that which beam, although I have said that you will be designing the edge beams, so all edge beams you will be getting one beam. Now I am just changing this thing, that no, your task will not be designing only one edge beam or one intermediate beam from all the maximum values. Rather than what you will be doing, that for each frame you will be designing the maximum value. Maximum required is, using that value you will be designing the total beam. That is, if you have got in this 2D frame, after analysis, if you have got the maximum is positive required for this beam and maximum is negative for this beam, so you will be using this maximum negative and this maximum positive for all the beams here. So this will you will follow this thing for all of the 8 frames. So for 8 frames you will be designing 8 beams actually. In fact you will be designing all the 8 frames, 2D frames. You will be obtaining the maximum positive required and maximum negative required, and those two will be using for all the beams in that particular frame. So 8 frame, if it is 8 frame, you will be designing 8 beam. So no edge or no intermediate beam in this case. Rather, you will have to design based on the frames. So that's how you will have to proceed for the flexural design of the beam. Now we'll be going for the shear reinforcement. We'll be starting the shear reinforcement and how to design those. To start with the shear reinforcement, I will be suggesting you to recall in your mind that what was the formula we have used. This is a very well-known formula, that is 2 lambda root fc prime bwd for the strength of concrete shear. So this Vc is nothing but the capacity of concrete in shear. So to illustrate this thing further, I will be drawing a beam which will clarify you this formula. So for example, this is a beam. In fact, it is a flange of the beam, and this is the web. In that case, we have got some shear reinforcement over there, some flexural reinforcement over there, obviously. This positive and negative reinforcements are there, and then the shear reinforcement as well. The shear reinforcement means in case of beam, it is actually the stirrup, sorry. So this is the stirrup, and this stirrup will have to design. This is the shear reinforcement, and other than that, this formula actually indicates nothing but the capacity of this concrete to bear. The capacity of this concrete to bear its you know what, the shear force. So the bending force we have already calculated using flexural strength. But what about the shear stress? This shear force in this section will be like acting like this as a whole. So for bearing this shear force, this concrete will take part in some cases, and the concrete capacity, that is we get it by this formula. But whether this concrete capacity is enough for resisting the shear force or not, that is our main concern. If it is not, then you will have to provide the additional shear reinforcement that is used in this figure as the stirrup, as you can see. So okay, so if we say the D, this D will be nothing but from the top of this up to the center of this reinforcement. That will be our D, as you know, and this width or the wave will be BW, and lambda that will be used as 1 for normal weight concrete. This lambda value depends upon the concrete property, and this Fc prime as well. This is the strength of the concrete, as you know, and obviously you will be using this as PSI value here, and that's why all this in inch to get the value in pound. So let's check what will be the concrete capacity for our case. So it will be 2 multiplied by 1 root 3000 multiplied by 12 multiplied by D was 18.5. So from this you'll be calculating this to obtain 24318 pound, which is nothing but 24.32 kip, we can say. So this is the concrete capacity, the nominal capacity of concrete. But although it is nominal capacity, while using, we always use it as 5 VC. And in case of shear, as you know, this phi value is 0.75. Whereas this was in flexural case, it might be 0.9, and it would vary from 0.9, and it might decrease as well. But for shear, we always use phi is equals to 0.75. So 0.75 multiplied by 24.32 kip that will give you 18.24 kip. So this is the capacity of concrete we'll be using to compare with the actual shear force acting upon this section. And now with which value we'll be comparing. For example, you will be getting by this time all the shear force values, governing values from your diagrams, the shear force diagrams you have plotted. So for example, this frame, you might have got the shear force diagram like this. Shear force diagrams, you have obtained the maximum values you might have obtained like this, or these diagrams may be in different shape as well depending on the type of load. This is actually for the vertical loads, gravity loads. For the lateral loads, you might be getting the different patterns as well. So whatever the pattern, it doesn't matter, but you will have to take the value of shear, where if I say this is the beam, if I draw the beam, this is the beam, for example, and obviously this beam is getting support from two columns like this, or if it is secondary beam, it will be going on another beam as well. So whatever it is, this is the beam. If this is the beam, and the diagram we are drawing actually, is this portion, that is the clear spans portion. We are drawing this diagram. Okay, so we are drawing this in clear span portion. In this portion we are drawing. Okay, so that if the diagram is like this, say for example like this, we have a diagram, for example, or if I draw like, say this is the typical diagram shape, this one and this one. So which value you will have to take? We'll not be taking this value or that value. So rather than we'll be taking a value which is at a distance d by 2 from this, point, that is the face of the support, edge of the support. So this, from this we'll be getting, after d by 2 distance might be this one, and that's why the maximum value we'll be taking, that is this value, and treat this value as VU. So this will go for all the cases of beam. At a distance of d by 2 you will be taking the value if this is the maximum value, and any other maximum value within the beam except d by 2, after d by 2 distance if we go, so any maximum value after that you will be taking. So in generally, if this pattern governs, then you will be taking the maximum value as at a distance d by 2, not within the d by 2. After d by 2 you will be getting this distance, particular distance, the maximum value of shear you will be considering, and while considering this VU, all the VU values you will be putting in the table for each of the beam, so that this is not only you will be getting for one load. After different combinations you might be getting this value as well, as we have got it for the flexural stress, flexural strength as well. We have drawn the tables, you know, and similarly you will have to draw the tables here as well. In case of VU, you will not have to take the positive and negative values, rather the maximum value, the absolute value, you will might be taking it for shear. That will be enough for us. So what we'll be doing, we have different combinations, and for different combinations we will be taking the maximum of those combination values as the maximum governing shear for particular beam. And for all the beam, what we'll be doing, say for example for beam 1, for beam 2, like this, and you might have got the from all combo 1, combo 2, combo 3. So from all this you will be getting the shear values individually. So for this one, so if you got the maximum value as 54, 65, 72, then blah 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 blah, then finally you will be getting the design. This is the absolute value, you know, absolute value. It doesn't matter whether it is positive or negative. The design value or design shear force will be, this is obviously in keep, will be, say for example, you will be getting the maximum 72. So for each of the beam you will be doing like this. Okay, so after all the beams have been calculated accordingly, you will be finalizing for each of the frame individually, as we have done it for the flexure. You will be doing the similar thing here as well. So for one frame, so this is one 2D frame, or for this 2D frame you will have to identify all of the beams with its identification number. So for example, if there B1, B2 and B3, but this is, say for example, B13, B14, then you will be comparing within these beams the values, the maximum design value within all these beams within a frame. Then we will take the maximum value of the shear, and accordingly that particular beam will be designing the shear force, shear reinforcement actually. So this shear force, the shear reinforcement, which will be designing based on the maximum shear force governing beam, that will be provided for all of the beam within that frame. And that's why for 8 frames, if there are 8 frames, you will be designing 8 individual shear reinforcement for the beams, and those reinforcements, 8 different patterns. For each of the patterns, one pattern of the shear reinforcement distribution will be given for all of the beams on that particular frame. So 8 different designs will be there, and that will be your task, similar to the flexural reinforcement. So now, as we are continuing, this was 5EC value, and this is the 18.24 we have obtained, that is the concrete capacity. So now some cases we will be analyzing, in which case how we will have to approach. So for our convenience, I will be giving some examples. So say VU might be 9 kip, for example. It might be 12 kip as well. It might be 25 kips as well. It might be 78 kip, and also it might be 150 kip as well. So for all these cases we'll be watching how to design the shear reinforcement individually. Although I know that you have by this time you have learned these things, but I will be clarifying this again here. So what is our concept here? Our concept in this case is very clarified. That is, the shear reinforcement, the total shear force, that is the VU, that will be actually taken by the shear force taken by the steel, the shear reinforcement, and shear force taken by the concrete. So using these two combination, that must be what we say, that should be equals to or greater than VU. That is our design concept philosophy here. So if you see that the concrete strength is enough to overcome this VU, then literally, theoretically, you will not have to apply any shear reinforcement at all. But in case you see that this 5EC, that is the concrete capacity, is not as much as the VU, then you will have to provide the additional shear reinforcement, which will, in combination with the concrete, will be taking and resisting the shear force VU. So that is our concept. But there is something to say further within this concept, and that's why we are giving example of different loads. So we analyze these things one by one. So if we go for the A, where VU is equals to 9 kip, in our case you see that 5 VC, that is actually equals to 18.24, as you have seen. So in this case you can see that this value 5 VC is well enough and greater than 9 kip. It's greater than 9 kip. But another thing, so literally you don't have to provide any reinforcement, the shear reinforcement VS, for supporting this VU at all, just because the VC 5 VC is enough to adequate to resist this VU. But you will have to check another thing as well, that is, you will, according to the code, it says that although if it is greater than, the 5 VC is greater than VU, you will have to again check whether 5 VC by 2 is greater than VU or not. Again you will have to check whether the 5 VC by 2 is greater than VU or not. Although 5 VC is greater than VU, again you will have to check even the half of the 5 VC is greater than VU or not. So for this, let's check 5 VC, that is 18.24 by 2, which will give you 9.12 kip, and you see that is again greater than 9 kip, that is the VU we have seen here. So if even 5 VC by 2 is greater than VU, then you will say that no stirrups, no stirrups will be provided. So practically you don't have to provide any stirrups at all. So for 9 kips, this is the method. Then B, where VU equals to 12 kips. In this case, again we can say that 5 VC 18.24 is well enough and greater than VU, but again you'll have to check whether 5 VC by 2 is greater than VU or not. In this case, you see 5 VC by 2, that is 9.12 kip, is not greater than 12 kip. Although literally this value is greater than VU and you don't have to provide any shear reinforcement in theoretical using theoretical concept, but the code says that if 5 VC by 2 is not greater than the VU, then still you will have to provide the minimum shear reinforcement within the beam, and that's why we'll have to provide the minimum reinforcement, shear reinforcement over this beam. And what will be the beam, how we'll be providing shear reinforcement? As you know that in shear reinforcement, in case of shear reinforcement, we don't actually determine the area of the shear reinforcement, rather we determine the spacing after defining one particular number of reinforcement. So spacing, there is a guideline. In case of spacing, we have the guideline for S max, whether just because the maximum, if I say this is the spacing or this is the spacing, which will have the greater amount of spacing, obviously this one. But if you are providing higher spacing distance is higher, then within unit region, the area of the reinforcement is becoming less. As much as you giving the higher spacing, the area of reinforcement you are providing, that is becoming lesser, rather than if you use the minimum spacings. As you decrease the spacing of the reinforcement, you will be increasing the area of reinforcement within a particular region. So that's why there is a guideline of S max, that beyond which you cannot go, so that the minimum reinforcement is provided here within using the maximum spacing guidelines. So that's why you will have to follow the S max here. So what is S max? S max, you have another direction for S max. For the time being, the general guideline we will be following, that is, I will be talking about the exception of this S max again after this example. But before that, see the general guideline. The S max, that is equals to, that will be smallest of, this is the smallest of, this is S max, but it will be the smallest of these three. What is first one? That is the formula AVFYT divided by 0.75 root FC prime BW, which must be less than or equals to ABFYT divided by 50 BW. So this is the first condition. S max must be smaller than this one, or it must be smaller than d by 2, or it must be smaller than 24 inch. So for these three conditions, whichever the smallest is, you will be applying that spacing. And for what? For a particular area AV, as you know, that is used here. If it is number 3 bar, then area of number 3 bar, you know, 0.11 inch square. But in this case, shear reinforcement, you will be using this multiplied by 2. You know why? Just because as we are providing shear reinforcement in a particular section, this shear reinforcement in this case, actually this is the shear reinforcement. So while resisting this shear force, it will be giving two areas, this one and this one, so double area will be provided. So we, in different purpose, you might be getting 4 and 6 times area. That is also possible in some cases. 4 or 8 number of times area you might be obtaining, but in general the shear reinforcement we use, in general we will be getting double area from a shear reinforcement. That's why AV will be the number of bar, area of that particular number of bar multiplied by 2 you will be using here, and the FYT, the yield strength of the transverse reinforcement, as we are saying, then FC prime the concrete strength, and BW the web width. You will be applying here D, you know, and 24, smallest of these three you will be using as S max, and this one you will have to provide in this particular beam where you have obtained this VU. Still after this 5EC, it is greater than VU, but not 5EC by 2 is greater than this VU. That's why you will have to provide this minimum amount of transverse reinforcement within this beam. Okay, and now another thing, now we'll be going for C. Now we'll be going for C, where we have seen that VU, that is equals to 25 kips, and in this case 5EC 18.24 is obviously less than 25 kips, and literally again we need what? You need to provide the shear reinforcement, that is VS, to overcome this VU in addition in combination with 5EC. So that's why you must provide VS in this case, and for VS we have a formula, and that formula will have to, so we'll have to provide, we will have to use the formula here. The required spacing will be equals to phi AV FYT multiplied by D divided by VU minus phi VC, and this is nothing but the VS actually. The required amount of load that will be carried by the steel shear reinforcement, that is actually this one. That is, if you subtract the concrete capacity from the VU, that will be obtaining the amount of shear reinforcement, shear force governed by the shear reinforcement VS. So this is the spacing. So if you use this equation, put the values here, phi obviously 0.75. If you use, say for example, we are using number 3 stirrups, then you will be using 0.11 multiplied by 2 multiplied by Fy, that is the yield strength of the transverse reinforcement. If it is, again, if we use, this is 40 ksi, so in this case particularly, if you use 40 ksi in ksi, then you will you'll have to put this value Vu minus phi Bc as kip as well. So you will have to provide this as like 25 minus 18.24. So all this in kips, then you can put this as ksi. Other than that, if you put it as 40,000, then you will have to provide this as well in pounds. And this D you will be always putting in inch, no problem about that. So D, that is 18.5, and that's how you'll obtain the spacing value. The spacing value you will be obtaining from here. You will be checking that. Again, you will have to check this value with this 3, the smallest of these 3. So for example, from this 3 you have obtained the minimum value is D by 2. So for example, 18.5 divided by 2, that governs the minimum value, that is 9.25 inch. This spacing governs the maximum spacing you can provide for this number 3 bars. So that's why 9.25 inch will be governing. You will have to check that whether, say, after calculation, see what you get from this. Let's see what we obtain from this value. So for example, we have obtained from there is for example, we have obtained from here 18 inch. So we will have to check it with all of these 3. So in this case we are not calculating this one. So for example, we have this one is governed. For example, just for example, as I cannot clearly speak this as we haven't calculated this one, but comparing these two, I can say this one will be governing here 9.25. So you will be comparing this S max. So S max is 9.25, and that's why you cannot provide with 18 inch here. Rather, you will have to provide number 3 stirrups at the rate of 9.25 inch center to center. That is the minimum spacing you will have to provide. Maximum spacing you can provide, but not beyond that. So that's how you will have to proceed. But one thing you will have to see, that is the VS value. The VS value, the S max, the formula S max, this one will be only valid. It will be only valid if this Vs is less than, if you see that this Vs is less than 4 root Fc prime BWD. The required Vs, that is if it is less than 4 Fc prime BWD. So again you will have to calculate this 4 root Fc prime. So let's calculate this one. Fc prime is 3000 BW 12 into 18.5. So you'll have to check it. The Vs, required Vs was required VS was, how we have calculated the required VS. So this one, after calculation, let's calculate this thing. 4 root 3000 into 12 into 18.5. So it will give you that 48,637, for example, pound. So 48.64 kip we can say. So if it is less than this value, VS is less than this value, then you can obviously using this formula, no doubt about that, but you will be comparing it with these three, unless this is greater than 4 root FC prime BWD. In case if it is greater than 4 root FC prime BWD, then you will have to go for another condition of S max, except this one what we have seen here. So in this case, again, as this VS, how we will be calculating the VS value? How to calculate the VS value? As we know that the VS is nothing but VU minus 5VC. So this amount, which we think that 7.67 kip might be there, which will be obviously you know what, less than the value VS we have obtained there. So that's why we don't have to use the VS, the S max for another formula, except what we have seen just here. So a little correction over there. What we are saying, that the equation of VS is not like as we have seen here. It will be VU must be less than or equals to 5VS plus 5VC. So this is actually our formula which we'll have to follow. So from this point of view, we can say the VS will be equals to VU minus 5VC divided by 5. So that's how you have to calculate the amount of VS. In previous case, whether you have shown this thing or not, VS. So yes, in this case as well, 5 VS, that is another factor must be compared with this one. The 5 VS plus 5 VC, these two will have to, in combination with each other, will have to overcome this value. That is what we'll have to follow. However, in this case as well, so therefore in this case, rather than calculating the value like this, we'll have to calculate the value VU minus VC, 5VC divided by 5. So let's erase this thing. Again we'll be calculating, although that will be also governing the VS less than 4 root FC prime BWD. So let's calculate this again. So VS will be VU minus 5VC divided by 5. So in this case, this will be 25 minus 18.24 divided by 0.75, and which will be giving us the value as 25 minus 18.24 divided by 0.75, and that is equals to 9 point something, so 9.013, and which is again less than the 4 root FC prime BWD we have obtained here. And that's why you will have to check this 18-inch with what? This 3, smallest of these 3. Say for example you have said 9.25 inch. So in that case you will have to provide this straight up here. So now we will be going for the fourth D VU equals to 78 keeps here. So 5EC 18.24, which is less than VU, so obviously additional shear reinforcement will have to provide. So calculate the spacing using the same formula, AB FYTD divided by VU minus 5EC. So this will be the spacing. If you use number 3 or number 4, whatever, accordingly you will have to use the AV multiplied by 2. As multiplied by 2, a double area will be working here. So now it will be calculate this thing, but while checking this thing with the S max, whether the S max will be this 3 among these 3, the smallest of these 3 or not, we'll have to check it with the VS. So VS, let's calculate VS for this one as well. VU minus 5VC divided by 5, and in this case that will be 78 minus 18.24 divided by 0.75, which will give you, if you calculate this thing, 78 minus 18.24 divided by 0.75, it gives you 79.68 kips, and which is obviously greater than 4 root FC prime BWT, 48.64. So greater than 4 root FC prime BWD. So if it is greater than 4 FC prime BWD, you will have to again check whether it is less than 8 root FC prime BWD or not. So what will be 8 root FC prime BWD? 8 root FC prime BWD will be double of this one, 48.64. 48.64, that is 97.28 will be here. 97.28 keep. So you see that yes, the 4 root FC prime BWD less than VS less than 8 root FC prime BWD. If this case governs, then you will have to check the obtained value of S with the S max of another formula. The S max here will be the smallest of again in this case ABFYT you will be using divided by 0.75 root FC prime BW less than or equals to ABFYT divided by 50 BW. This one is similar to the first one. The second one will be changed like D by 4. Third one will be changed as 12 inch. So smallest of these 3 you will have to, as it is like this, you will have to check this one with this obtained value in this case, but not this one again, just because the VS required is within this range. within this range, say for example. That's why we'll have to use this value. Check this one. So in this case again, let's say it will be 18.5 divided by 4. That will be 18.5 divided by 4. 4.625 will be the minimum spacing you will have to provide in this case. And that's why even if this one you might obtain 10 inch for example, but still you cannot provide this one, then you will have to provide this one. So number 3, stirrup at the rate 4.625. so if you round it further, like you will be giving 4.5 inch center to center like this. So that's how we will have to provide shear reinforcement here. And what will be in case VU equals to 150? In this case, 5VC again less than VU, no doubt about that, and VS, that is VU minus 5VC divided by 5. You will obtain this thing, that's 150 minus 18.24 divided by 0.75. Which gives you 175.68. And that's what, as we have calculated 8 root FC prime 97.28, it is well beyond that. So it is greater than 8 root FC prime BWD. So in this case, the code says you that although we can provide from the theoretical requirement we see, we have to provide shear reinforcement in such manner that that will be able to carry this load. But no, according to the code it says you cannot design as it is greater than 8 root FC prime BWD. As it is greater than this one, you cannot resist the load of shear using shear reinforcement, as the concrete capacity is very less than the required VS, and required VS is very larger, even if I can say that it is almost greater than VS required is 8 times greater than the capacity of VC. And that's why we literally, although we can provide and we can overcome this with the shear reinforcement, but code says no, you cannot provide this, rather you will have to change the section. If you change the section, the beam dimension, if it is increased or width or depth is increased, the area will be increased. And that's why the VC formula, you know, there is BWD, or if you increase the strength of the concrete as well, root FC prime, all these three in combination, the VC will be increased. And as a result, if VC is increased in such a manner that the required VS will be less than 8 root FC prime BWD, then you can design with that particular section. Other than, you must change the section. So I think for your case, as you are assuming enough depth for the concrete beams, so it might not create any complexities, and it will not be exceeding 8 root FC prime BWD in any case. And in most of the cases, you might be watching that your value will be minimum reinforcement is required, or no reinforcement might be required at all, or even if it is required, that will not go beyond even 4 root FC prime BWD, I hope. And and that's how you'll have to design. But in case if it is exceeding this, then you must change the concrete properties, the strength of the concrete, or the dimension of the concrete you must increase so that it can resist the shear force. So that's how you have to provide the shear reinforcement. And I have said that from the calculation, the maximum for 8 frames, for 8 individual 2D frames, if you have 8, that is better. If you have 10 or 12, as much the number of frames you have got, for each frame the maximum shear value, taking that value you will be designing the shear reinforcement distribution accordingly for all the beams of that particular frame. So the number of 2D frame, the number of shear reinforcement design you will have got. And for all of the designs, 8, if you have 8 individual designs, then you will have to provide 8 individual longitudinal section, 8 individual section you will have to provide with shear reinforcement like this. So for example, you'll have to provide this shear reinforcement like this for longitudinal section, and also you will be taking one section over there. If it is support, it's at a sufficient distance, but not close to the mid section. You will be taking one section, say at a distance, if the total length of the beam is L, you will be taking a distance L by 4 from the face of the support approximately. Then you will be taking a section, the similar section you will be getting from there, so no need to draw another section there. So one section there and another section you might be taking L by 4, approximately L by 4, no, L by 8, okay, or even you can take another section at the middle of the shear reinforcement. Okay, no problem at all. So at the middle of the section you can take another section. So for each of the frame you will be getting one design, and for one design you will be drawing one longitudinal section and two section what is at a L by 4 distance, and another at the middle of the section, and that two sections you will be drawing like this. And obviously this section as well, just because if you draw, although this will be similar, just because the negative moment, flexural moment, the maximum negative flexural moment you have provided for both of these two supports, that's why you can obviously take any of these two. So okay, two section will be enough. If you give 3, I wouldn't mind, but 2 section minimum will be required. That is, one is at a distance L by 4 and another one is at a distance which is the middle of the beam. To 2 sections you will have to again redraw this thing, and these 2 sections for each of the frame and one longitudinal section. That will be your task. Okay, so that's how you'll have to design it and submit it in the next class. I don't think I have missed anything. If you have any queries, then we'll be answering after this lecture ends. So thank you for this time for this class.